In this video, I'm going to attempt to explain basically what is integration. So this is the introductory video into integration, and it's going to be more of a conceptual video more than showing how it's done, because it's important to understand what it is before you learn how to do it. So I have some variables. This is sort of like a physics problem. So if you haven't taken physics, don't worry, I'll explain through everything. But this v here is speed. This is time, and this is distance. So basically, I'm just asking here, if an object is going 6 meters per second in a straight line for 7 seconds, what is the distance? So the formula we would use would be speed equals to distance over time, right? Hopefully you've seen this before, either in a physics class or in your math class. Pretty straight idea, right? Because I have meters per second for my speed, and then time is in seconds, so the distance would be in meters. If we want to find distance, we can just rearrange this. So we can say distance equals to v times t. V, we know, is 6 meters per second. Time is 7 seconds. The seconds cancel out. 6 times 7, 42 meters. So that is the distance traveled by some object. Pretty straightforward. But what if I wanted to represent this problem on a graph to sort of show it geometrically, to understand what are we doing if we were to look at this, if we had a shape? Or in other words, I guess you could say is, what if I was describing this as a function? So let's say v, this function v, which I said was 6 meters per second. Let me put it on a graph. So it's going 6 meters per second for 7 seconds. So it would just be a straight line from the 6 meters per second mark, because this is in meters per second and this is in seconds. So this would go straight like this, and then it would end right here. So we could sort of do like this, like a discrete function. So we have this thing, and I'm just going to draw a dotted line from this 7 seconds mark to show that thing. And so here I have represented the function, which is speed, going for 6 meters per second on this graph, where v is my y-axis, t is my x-axis. So if we look at this, we can see that this is a shape. This actually looks like a rectangle or a square. I'll call it a rectangle, because I'm not sure if it's exactly, well, actually, no, it's not really a square because the dimensions aren't the same. So this actually looks like a rectangle here, which is interesting. Now, what if I asked you to find the area under this function? What would that serve? Well, what is the point of finding the area under a VT graph? So if you've taken physics, you know what I mean. This is a VT graph, which just means plotting velocity with respect to time. That's basically it, right? If I asked you to find the area, what is the point of doing that, right? So pause the video and think about that. Well, to start, we know that area is length times width, right? So let's say, it doesn't matter. I can call this length. I can call this width. If we found the area under this graph, it would actually give us the distance. Now, how does that make sense? Well, if we look at the dimensions of this rectangle, we have time here, and we have velocity here. And we just did velocity times time, where the units cancel out, right? So, in other words, our area here, area equals to length times width, which would be length, I'm calling a velocity here, right? Length, velocity, and my width here is going to be time. And we plug it all in, this would be 6 meters per second times 7 seconds, which gives us 42 meters. That's pretty interesting, right? If we were to put a function on a graph and we found the area underneath, it can tell us something about the relationship going on between the independent and the dependent variable. So this is actually the idea of integration, to find the area under a function. That's one way. Another way is for the applications of integration, but the idea of integration is just finding the area of a function to discover what I like to sort of call is how much of some function. And what that means is sort of like the sum of like the function up till a certain point. So let's say let's say I had a function uh, starting from the origin, ending at some point. Origin, this is my y, this is my x-axis, and this modeled the rate at which coffee is being poured. So the units on the y-axis would be milliliters per second, and on the x-axis it would be just seconds. So x is time, and then the y is the rate of change, the rate at which coffee is being poured. If I wanted to find the area underneath this curve, right? It's really hard to come up with some shapes, but if I try to put random shapes in and then add up all the area of those shapes, you know, what I'd be doing is I'd be doing milliliter over second times seconds, which just gives me milliliter. So I could figure out how much coffee has been poured into a cup over the entire thing. So if this function models coffee, or I'll just say rate of change, right? If the function represents rate of change, then this can just represent the how much part. How much coffee has been poured into the cup, if that is my function representing that. So hopefully that sort of makes sense. I used a physics problem originally, and now I showed you another simpler problem. So I want to dive basically right into the intuition of it. So let's say we had this function f of x, and I wanted to find the area between a and b. So a is my like initial boundary, and then b is like my final ending boundary. So a long time ago, this was again a thing mathematicians were looking for. They're like, okay, how do we find the area under the curve? Because they understood the significance of finding the area under the curve. And so what they started to do was, well, what if we sort of did like approximations? And you can do approximations by drawing like rectangles. So let's say I draw like a rectangle right here. Rectangle here, 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 rectangle, here, here. Basically, like I'm just trying to approximate as much as the area as I can, right? And so I can call like this distance, this width right here, delta x1. Delta because it's a change in the position, right? If you, I keep mentioning this, but like if you've taken physics, you would know the meaning of delta perhaps a little more, but maybe not. You probably already know that even if you haven't taken high school physics. But delta just means change, right? So change in position. So I could call this like width here. This, I'll write it in here, width. Delta x1, and then I can call this width here delta x2, right? The width here. And then I can call this delta x3, and so on until this point. I'm going to just scratch out the b and write actually no, I won't scratch out the b. This is getting a little messy. Apologies here. Let me just undo some of the shadiness. Until this very end point, delta xn, where because you can have as many like widths as you want, as many rectangles as you want. This is like just like a simple representation. We can draw different kinds of rectangles, different kinds of shape to best get the area under the curve because we're just approximating the area. And then we can say the length here is some value of f of delta x. But I will just say, I'll say f of xi. So the length here would be f of xi. This I just means like I some value of, because what I'm gonna try to do here is gonna come up with a general formula of if I could find the area of every rectangle and then add it up, I could get the approximate area under the curve, right? So what I'm trying to achieve here is if I could do the area of this plus the area of this plus the area blah 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 and so on, and like we can say this is delta x1, delta x2, and this is in general just a general length of xi, whatever, right? We can get the approximate area, right? And there's a way to sort of express this, and the way to express this would be something called sigma notation, because what we're doing is we're summing up a bunch of numbers. We're getting numbers from the individual rectangles by multiplying the width and the length to get the area of every rectangle, and then we're adding all the areas up to get an approximate area. So we're going to take a brief transition here into something called sigma notation, so I can illustrate what I want to talk about. So sigma notation is, first of all, sigma is this big E looking thing. That is sigma. Now in sigma notation, you can use it to like sum up numbers, sum up like a sequence of numbers per se. So here's how it would look. Let's say we had AI. AI is some sequence where it's 1, 2, 3, 4, 5, and so on. Into some general condition, but I won't write that. And this would be the first term, this would be the second term, this would be the third term, the fourth term, and the fifth term, right? Hopefully you can see that if I draw like lines like this. Yikes, that looks horrible. I'll leave the lines out, right? So those are the different terms. So the way we would write sigma notation is, first we put the E, which is the sum sign, and then you put the sequence you would like to add up. So actually, let me keep it consistent with the colors. Let me put this blue here. And let's say we wanted to find the sum of numbers from terms 3 to 5. So third to fifth terms. We want to find the sum. And so again, this guy just means sum here. So the way we do that is, at the very top of this E, the sigma, we're going to put the final boundary. Now the final boundary here would be 5, because that's the fifth term. We want to add stuff from the third term to the fifth term. So we first put 5 up top, and then we say I, because we have an AI here, equals to 3. So what this means is, we would say A3 plus A4 plus A5. So this, just again, to reiterate, this is the final term, and this is the initial term, right? So initial, think I equals to 3 term. So this is a general way to explain, let me just erase this. This looks a little confusing. So this is a general way to describe a sequence of numbers if you wanted to sum certain areas. So that is a sigma notation. So I hope that makes sense, because now we're going to go back into the approximate area problem I was talking about to show where this would come handy for us to understand integration. So I mentioned earlier the approximate area thing. So we could represent this with sigma notation. So we can say this E symbol here. And let's start off with the boundaries. So we said the final boundary would be n. And you may be confused, where is this n coming from? This n is coming from this n right here, delta xn, because we said the widths could, the position in x could be changing. So delta x1, delta x2, delta x3, all the way to delta xn, some general form. And our initial boundary, what we like to do is we like to do I, and then say I equals to 1, right? So now we've sort of set up the parameters for this way of approximating the area. Now we're dealing with rectangles here, so we're going to do length times width. Our length, we said, was f of xi, fxi. And our width, we said, was delta xi. And so hopefully, let me just actually erase this little circle at the end. That might confuse someone. So that's, so again, this is just using the sigma notation we used before. So this is the length, this is the width. Now, if you notice something, if you remember, the I is the initial boundary. So I equals 1, that would be plugging in 1 and 2. So that would be f of x1 times delta x1, right? And then we do plus, so maybe I should write it out. So this would sort of look like, as an example, this would be f of x1 multiplying delta x1. So I said plus, multiply, I think. This is a little... Okay, sorry. I have horrible handwriting, as you can probably have already figured out by watching my videos. Delta x1, because we're just plugging in I equals to 1, plus, and then we'd go on and on. We would say f of x2 multiplied by delta x2, and we can go on and on to describe it in some nth term, right? So that's how you'd find the approximate area. That's basically it. That's like a general formula finding the approximate area. But what if we're not satisfied with that? We want to be as accurate as we can. So how can we find the actual area? No approximation, just the real thing. So you can draw as many rectangles as you want, but ultimately you're not ever going to be able to really realistically get the perfect rectangle underneath the curve. Because as you can see in this diagram I've drawn, or this graph I've drawn, my rectangles are going over the curve a little bit, like here and here, a little here, here, here. So they're not exactly underneath the curve perfectly. So we could, in theory, if you could try to imagine, we can have like an nth amount of rectangles that we could draw, like an infinite amount of rectangles we could draw to fill up all the space under the curve without going over the curve or outside of the limits. In other words, an nth amount or an infinite amount would mean the same thing we just described of f of xi multiplying delta xi, but we put the limit, a limit as n approaches to infinity. So you can see here, we're recalling from our grade 12 calculus class, limits are coming very important again. And this formula, this little messy looking thing, is the definition of the integral. That if you were to take an approximate amount of rectangles and say to the nth amount of rectangles you could have, this would be the definition of an integral. But I'm not going to write out integral. I'm going to show you the integral sign. So the integral sign looks like a crowbar, like this. And then what you would write is you'd write out the function. So the function here is f of x. And then you write dx, because that is the variable with respect to. Now, we're not done yet. At the top and at the bottom are your boundaries. So the top boundary is the final boundary. So you'd put b, because if we look here, we were originally asking, find the area between a and b. So the top we put b, and at the bottom we put a. This is called a definite integral. Definite integral, because the boundaries have been defined. No, not integrals, integral. If there were no boundaries, like let's just say f of x dx, this is an indefinite integral, because there are no boundaries. So you could describe the area in a general formula, which is pretty cool. And then if you wanted to find the area between certain points, you just plug in certain points and then solve. So this is the very definition of an integral. So I've not showed you how to use the integral, how it works. I will do that in the next video, but hopefully this made sense. This idea of, again, having like a bunch of rectangles in there, and then we're putting a limit because, you know, we want to maximize the amount of number of rectangles we can without going over the curve or past a certain interval. Like, you know, you don't want to go past A or you want to go past B. You want to stay in there and you want to stay under the curve to get the best area you can. And you do that through this formula, but we can just describe it as this integral sign. So this integral f of x d of x really symbolizes this thing. So hopefully that made sense. And in the next video, I'll go through how to basically use the integral sign and how it looks like and certain rules we have to observe to find the integral. But that's really it. That is the beauty of this part of calculus, the idea of finding the area under the curve or some function. It's just so helpful to basically any problem we can solve. So I'll see you in the next video. Hopefully you enjoy this. Take care.